I welcome you guys to our last section in chapter 5. So this is where we're going to apply everything that we've learned about logarithms and exponentials, specifically solving exponential equations in this section. Okay, so we've talked about how there's lots of different applications to exponential functions. We have population growth. We have half-life of maybe if you're a nurse or a doctor of certain medications in the bloodstream, half-life of radioactive elements. We have finance. So in the equation PERT, which we're going to see for continuously compounded interest, we have exponential growth there. Just, it's all over the place. Okay, lots of different areas that we have this exponentials, even down to like forensics. The cooling body problem. So Newton's law of cooling, which uses exponentials, also helps us figure out, how long ago a person has passed away based off the temperature of their body when found, and the surrounding temperature as well. So it's just the applications here. There's just so fruitful that I'm glad that this textbook takes time to just dedicate a whole section to word problems for this type. All right, so here we go. Let's take a look at a few of these different ones. So this equation is pretty much the equation we're going to be using for everything. Okay, and it's going to change it's like what you might be calling this here. It's P of T because we're talking about population, but that might change depending, but they'll all have this same basic structure. Okay, so let's go through what each one of these pieces stand for. Okay, so P of T, that's the left-hand side here. That's going to be the population after T years. This P naught, this P sub 0, that's going to be the initial population. That subscript of 0 tells us that time is 0. So if time is 0, then it's the beginning or the initial population. K is going to be the exponential growth rate, and T is going to be the time in years. So it says the unit of time can change, but must be consistent throughout. So you'll notice up here we said the population after T years, well, then our time better be in years also. Okay. All right. In 2013, the population of Ghana, located in the west coast of Africa, was about 25.2 million, and the exponential growth rate was 2.19% per year. Find the exponential growth function. Okay, so I'm just going to write out that equation that we had on the last slide, and we'll go through here and we'll see if there was anything that we can fill in. Okay. So it says in 2013, the population was about 25.2 million. Well, we're going to let that be our P naught, our initial population. So what that means is that we're letting our beginning of time be 2013. That's what we're going to let be the beginning. So if, for example, later on, it's like 2020, then my time would be 7, since it's been 7 years since 2013. So the second that we let this 25.2 be our P naught, then we're saying this is the beginning of time right here, okay, for this equation. And then it also gives us the exponential growth rate. Now, all of our growth rates are going to have to be changed from a percent into a decimal. So this is 2.19%, but we're going to have to move the decimal 2 places to the left. And so what that's going to give us, that's pretty messy there, you guys. My percent sign doesn't even look like a percent sign. Let me try this again to give myself a little space. So 2.19%, if we move that decimal 2 times, then what we're going to end up having is 0.0219 as what we're going to use for K. So never substitute in the percent. You've always got to change the percent into a decimal. All right, so we're ready to write a exponential growth function that somebody could use to model the population of Ghana after 2013. So this is the answer to that. So how this works is somebody plugs in any time they want after 2013. And this will spit out the population of Ghana. And that's exactly what we're going to do here. Okay. So I'm going to go ahead and rewrite that model here. All right, so it says estimate the population in 2018. Well, all we need to figure out is what the T is, right? Okay, so what should we use for T? It's going to be our question. So remember, T stands for the number of years since 2013. So let's go out of the way. If it's 2018, it has been 5 years since 2013. So T equals 5. Okay, and if you're struggling because it's like a big one, you're just subtracting there, right? We're saying, okay, 2018 take away 2013. That's how we got the 5. So we're going to go ahead and substitute 5 in. So P of 5 equals 25.2 e to the 0.0219. And now we're going to substitute 5 in there. All right, so let's go ahead and go. We're going to be using our calculator a lot this section. So if you don't have your calculator with you, now's a great time to go and pull it out, okay? All right, so let's go and see what that is. Okay, so 25.2. And then E, so shift E, and then 0.0219 times. And if you're getting something smaller, you know you messed up because we have this as the growth rate, which means that this is grown. So we got 28.1. We'll just kind of estimate. They didn't tell us where to round it, so we have that freedom there. So that would be, if we were to kind of sum this up, okay, the population for Ghana in 2018 using this model would be, we'll put approximately, kind of save ourselves a little bit, 28.1 for this model. This is an old textbook, so sometimes it's kind of fun to go in and see what the actual population of Ghana was, because we've had the census since then, right? So that might be something that you go and look up and see, well, how close were we to it? Okay. After how long will the population be double what it was in 2015? Okay, so here's our model. Write it again. Well, it was 25.2. So double that would be 50.4. So that's what we're going to substitute in over here. So this shows the population doubling. We started off P naught, the initial population, with 25.2. And after some time has passed, P of T, it's up to 50.4. Now notice that the only variable that we have here is T. That's the only unknown that we have here. And that's exactly what we want, because it says after how long. In other words, find the time. So we're just going to solve this for T. All right, so let's go ahead and start by dividing by 25.2 to both sides. So remember, when you're solving exponentials, first thing you got to do is isolate the exponential. And this is, of course, 2, because that's how we got the number. So let's see here, we got E 0.0219T. And then to get rid of E, we're just going to natural log both sides. Whatever you do to one side, you got to do the other side. So we have natural log of 2 equals 0.0219T, and then divide by 0.0219, and you got your time. Now resist rounding anything until the end, Because if you use a rounded answer to get an answer, increase the error. All right, so let's go ahead and go to our calculator to get this. So we have natural log of 2 divided by 0.021. So we have 31.6, it looks like. Let me go back and double check. Yeah, 31.6. Okay, so approximately what? 32 years there? Okay, these are all approximates. We're going to be doing a lot of rounding today. Okay. All right. Actually, that 6 should be what? The 5 rounds it up. It should be a 7. Let's make 5. They didn't tell us where to round. Okay. So after how long? So 31.7 years. At this growth rate, when will the population be 40 million? Okay, so we have our model, so we're going to continue to use that one. So we're going to substitute 40 in for the population, and we'll solve for the time. Okay. So remember, just to kind of give us some setting here, it took 31.7 years to make it to 50.4. We're only wanting 40. So it should definitely be less than 31.7 years. Okay, so let's go in here and do the math. The same math we did last time, guys. And now I'm just going to leave this. I don't want to round any answers along the way. So then we'll natural log this whole thing. And again, just keep this like so. The very end is when we'll round. Okay, so we're going to divide by 0.0219 to both sides. And that should give us our time, approximately. Okay. All right, natural log of 40. So we'll put this guy in. Natural log of 40 over 25.2. And then this, oops, that's not what I need to get out first. There we go. And this whole thing is divided by 0.021. 20.557. How about we just put 20.6? And we expected something smaller than 31.7. So this sounds about right. Okay, so that was an example of population growth. Let's take a look at some finance type stuff. Okay. So it's the same equation, you'll notice. Okay, but this, it's not really talking about a population, it's just talking about the amount in an account. So anytime that you see a problem that says continuously compounded interest, that's when you'll be busting this out. In other textbooks, just to point it out, it looks like this. PERT. So my teachers, when I was going through school, said use the PERT formula. Okay. P stands for the principal, the original amount invested, or P naught, the beginning amount. And sometimes we don't use K, we use R for the rate. You can see it's the interest rate, so why not call it an R? But in the spirit of your text, wanting you to use this for every type of problem, I will do it that way. I just wanted to make sure that you knew that PERT and this are the exact same thing. Okay, so I'm going to go ahead, write this down. Hold on, I'll get them actually. Go to the next slide first. Okay. So before I do that, let's go over what each P stands for. So P naught is still the initial. Last time it was the initial population. This time it's the initial amount. So maybe you're borrowing or maybe you're investing. Okay, but it's going to be that beginning amount when time is 0. Whereas P of T is going to be the amount after T years. And these are usually in years because when you're given a rate, like if you go to the bank or something, they give you the APR, which is the annual percentage rate. So rates are usually given in terms of a year. So you want to keep your units consistent throughout. So it will be years all the way throughout. All right. So I'm going to write that down. So P of T equals P naught E to the KT. Suppose that 2,000 is invested at an interest rate K, compounded continuously, and grows to be that $2,504.65 in 5 years. So the keywords are compounded continuously. That's what tells us to use this equation right here. Okay. All right, so we have to figure out what's going to get substituted into certain spots. Well, 2,000 is the initial amount, so that's going to go in for P naught, P sub 0, when time is 0. And then the other amount is going to be the amount after 2 years. So it's going to go into the P of T. And then clearly 5 is going to be the time. Okay. So we're going to go ahead and substitute those in. Let's see what we get. We don't know K, but we do know the time is 5. Okay, so we have to solve this. So we're going to go ahead and isolate the exponential. So divide by 2,000 to both sides. And this I'm just going to write instead of K5 as 5K. And then, of course, to get rid of the exponential, we will take the natural log of both sides. And then our last step is just to divide by 5. So there's our K. And that's what it wants to know. What's the interest rate, right? Okay, so let's plug this in. Natural log 2504.65 2,000. Oops, I keep doing that. Sorry, guys. I'll learn eventually. All right. And then divided by 5, the whole thing, right? So I got 0.045-ish. Okay. Yeah, that's good. All right, now, usually if you go to the bank, though, they'll move the decimal back to give you the percent. So this would be 4.5% annual percentage rate. Either one's fine. It just depends on what the word problem, you know, how they say they want the answer. I wanted to show you both because I know usually we talk about them in terms of percents. Find the exponential growth function. So we have this, the amount in the account at any given time is the initial amount e to the KT. Well, we know the initial amount invested was 2,000. And we just found out that 0.045 is the rate. So here's a model that somebody could use to find the amount in the account at any given time. And I suspect that that's what we're going to do right now. So we're going to find it after 10 years. So let me just rewrite that. So we're going to substitute 10 in for the T and just go to our calculator. And in this case, they don't have to specify where to round. We're talking about money. So we know that we're going to round to the nearest cent. Okay. So let's go ahead and type this in. 2,000 e to the 0.045 times 10. All right, 31. 36, let's go through the change. 62 cents. This 4 right here is going to keep it at 62 cents. So 0.62 There we go. That's how much we would make in 5 years. This is pretty good. Or no, I'm sorry, in 10 years. Sorry, guys. I was looking up here. In 10 years. Okay. After how long will the 2000 have doubled? Okay, so here's our equation. Now, if it's doubled, we started off with 2000, so now we should have 4000. Now, let's go ahead and solve this. So we'll isolate the exponential. Four thousand divided by 2000 is 2. And then we'll just go ahead and take the natural log of those sides. And then we'll divide by 0.045. Okay, let's see here. Natural log of 2 divided by 0.045. 15.4 years. Yeah. Now, what I want you to notice is that to find the time here, if you really want to think about this, we had natural log of 2 divided by this 0.045. That was the K. Okay, so the time was just natural log of 2 divided by the K. That's going to lead us into what this is saying right here. The growth rate K and the doubling time capital T are related by. We actually just used this right now to find the doubling time. And actually, if you go back and you check, I think it was the population of Ghana problem, right? After how long will the population be double what it was? Well, check it out. We did it again. Natural log of 2 divided by K. This was our growth rate, K. Check it out right here. It's in the K position, right? Okay. So we've actually just kind of derived the fact that this is true. And if you work with it, you could find the other, let's just work with it really fast, okay? Often in this class, we multiply by the denominator to get rid of the fractions, right? So now we have KT equals natural log of 2. Well, if we divide by T this time, instead of by K, then you have that the K is natural log of 2 divided by T, which is this other formula. So this is only for doubling, okay? So when you're looking for the doubling time, you got a shortcut here that you can use to find either the K or the T. All right. The population of the Philippines is now doubling every 37.7 years. What is the exponential growth rate? So we probably want to use this formula because this one finds K, the rate. Okay, so we're going to go ahead and put in the time, 37.7. And then we'll just have our calculator spit that out for us. Make sure you're closing those parentheses on your calculator. You could be getting these wrong. Okay, so 0.0183. We're going to move the decimal place twice to turn it back into a percent. 1, 2. What was after the 3? Oh, 8 was after the 3. Okay, so let's put the 8 there. Okay, so K is approximately 1 point. Now this 8 is going to round the 3 up. So 1.84% could be another way to look at it. All right. So nice and easy with these formulas, it makes it super fast. Now, when we first started, we did a population problem using an exponential growth model, which exponential growth is really close to this. It looks like it matches it for a while, and then it kind of takes off to infinity. So the difference between the two is that this one, you know, stops and starts to flatten out. It has a horizontal asymptote. So logistic growth is actually a more realistic model quite often because populations can't head off to infinity. All populations, their environment has a carrying capacity. And so that's what this shows. This shows a limiting value here. Like, okay, it's not just going to go off to infinity. It's going to try to grow fast, and then it's going to slow down in its growth because it's starting to run out of resources, run out of room, whatever. Okay. All right. So it says right here that that carrying capacity, that limiting value, is A in the equation. So this top number is going to be what the population will approach. Okay. So in other words, as time goes to infinity, the population should approach A, is what this is saying in mathematical notation. So this is called logistic growth. It starts off the same as exponential growth. So exponential growth models are good to use in the short term, but they're usually not very accurate if we're talking about long term, if time's going off to infinity. A lake is stocked with 400 fish of a new variety. The size of the lake, the availability of food, and the number of other fish restrict the growth of that type of fish in the lake. The population of fish in the lake after time t in months is given by that function. What is the limiting value or carrying capacity of the lake? Well, we said it's this top number, right? Okay, so there's going to be 2,500 top possible fish of whatever variety, whatever this type is we're talking about. They never specified. Find the population after 0, 10, and 20 months. Well, they're keeping the units consistent. It does say up here that t is in months. So we can just substitute these in one at a time, right? Right here, and have our calculator get it for us. So for p of 0, this is what we will be substituting into the calculator. We'll see what that gives us. Then we'll do it again for 10 months. About 10 is. And we should be expecting this to grow. It is a growth model. So each time it should get higher. I can kind of check and see if we made any errors maybe when substituting it into the calculator. Okay, let's substitute these in one of them. All right, we got 2,500 divided by parentheses 1 plus 5.25, and then e the negative 0.32 times 0 close parentheses. So 400. That makes sense, right? That's, what did it say up here? A lake is stocked with 400 fish. So when time is 0, when we first started, we have 400 fish, and that's what our model is showing. So this makes complete sense. All right, let's go in there and just change that guy to a 10. Oops. Yeah. All right, I'm gonna insert a 1 for 10 there. All right, so we're getting approximately 2,059 fish. Go check out if we put a 10 in there. I mean 20 in there. 2,478. So it grew. So this is good news. Probably did that one correct. Now for the rounding, you guys don't get tripped up on the rounding. If you're on my math lab, it's going to be super specific. It's going to say round in this digit. So you'll know, okay? So don't stress on that portion of what we're doing here. Verify that the carrying capacity is the answer in part A by letting the number of months be 1,000. So that's a pretty big number, 1,000 months. So we're going to substitute that in. And let's see what we get. The population after 1,000 months. My other calculator just spit out 2,500. It was like already there, but I'm not sure. Let's see where this one's set at for its, oh, hold on. Push up arrow. Will it bring it back? Yeah. Okay, so then let's just go in here. Put 1,000. Yep, this one says 2,500 also. So that looks good. Okay. All right. So that if the carrying capacity is 2,500 or the limiting value is 2,500, then we should expect, you know, to get so close to that we're basically 2,500, you know, at some point. And so that's why we plugged in an extremely large number. And that's why we got, it's probably not 2,500 exactly, but the calculator's kind of set to round. And so it's all, you know what, close enough, spit out 2,500. Okay, so everything we've done so far has been exponential growth. The only thing that changes for our exponential decay model is that we have a negative on our growth rate. Okay, that's the only difference. Everything else stays the same. This is the amount after some time. This is the initial amount. K is the rate, T's time. Okay, our graph changes, of course, to look like the exponential decay model that we've talked about earlier. So some instances where we use this. So on the left-hand side here, we got some radioactive elements here, right? And I put down their half-lives. So I put down some that have quick half-lives, 1.1 seconds, 6.71 days. Then I put some things that have longer half-lives. Wow, these are getting pretty big. I also put medications in here, like the half-life. So acetaminophen, you know, how long before it becomes half. So half-life just means, like, let's say that you took 8 milligrams of something, right? Let's say acetaminophen, then 2 to 3 hours later, you should expect half of that. So you should expect 4 milligrams, okay? For these various caffeines, for these various medications, caffeine's on here too, right? You drink 7 ounces of caffeine in 4 to 5 hours, you'd be down to half of that. So 3.5 ounces, whatever. Well, all right. And probably have, I don't know how many ounces of caffeine. That's the coffee, huh? So I don't know what percentage of that is caffeine. So forgive me for that. But hopefully you understand what half-life is. It's how long it takes for it to reduce down to half. Okay. All right. So we have these, turns out, these same exact formulas that we had earlier, where if we want to find the rate, it's just natural log of 2 divided by the doubling time, or in this case, the half-life time. Okay. And then if we want to find the half-life, we could just take natural log of 2 and divide it by the rate. Same exact formulas, whether you're doing doubling or you're doing half-life. A radioactive element, carbon-14, has a half-life of 5,750 years. The percentage of carbon-14 present in the remains of organic matter can be used to determine the age of that organic matter. Archaeologists discovered that the linen wrapping from one of the Dead Sea Scrolls had lost 22.3% of its carbon-14 at the time it was found. How old was the linen? Okay. So we're going to go ahead and write down the formula for exponential decay. We know this would be decay because we start off with 100% of its original carbon-14, And then it says that it lost 22.3%. So it is decaying. So we're going to put a negative on that K, you guys. All right, now this one's kind of tricky because remember, this is the original amount and this is the amount after some time has passed. So one way to kind of think of it is it's going to start off with 100% of its carbon-14. Okay. And then for the amount after some given time, well, let's go see here. If it starts off with 100% and it lost 22.3%, right? So 100 minus 22.3. Oops, realized I wasn't doing anything. There we go. We got 77.7. So this is the amount that's left. Now remember, this is the amount that's left over here. This isn't the amount lost, okay? So this is 77.7. You can move the decimals on, but if you move it on this, you got to move it on this one too. So I think it's easiest to just be like, okay, 100 here, 77.7, okay? All right, now we need the K. We don't have the K yet, okay? So let's go and use that formula to get it. Remember, K equals the natural log of 2 divided by the half-life. So natural log of 2 divided by 5,750, okay, is what we're going to put there. And there is a negative on it, okay, from the formula. Let me just see how gnarly that is. Natural log of 2 divided by 5,750. Pretty gnarly. So I'm just going to leave it as is, you guys, because I don't want to turn that. So that's fine. Okay, so let's go through the solving. Let's kind of recap first, though. We started off with 100% of it, and after some time passed, we ended up with 77.7% of it. Okay. Remember, this is the initial amount, and this is the amount after time has passed. All right, so we're going to solve this how we have been, isolating the exponential. So we've got, when we divide that out, just to make it a little easier, we did that. And then we're just going to take the natural log of both sides. And then we'll divide by that entire fraction. All right, so here is what we're going to put into up here. Holy moly. Okay, let me go try to put that. Oh, I closed it out. Put that up again. Let's go put this in. Natural log of 0.2, those parentheses. So then we've got negative natural log of 2, close parentheses, another fraction. 7. So 2,093 years. That's how old, what does it say at the time it was found? So that was how long ago, or how old it would have been at the time it was found, right? Okay. How old was the linen wrapping? Okay, cool. Just making sure we answered everything correctly for you guys. All right. Another decay. So in this case, it's talking about a car's value decreasing each year after purchase. So you would know you would be using a negative on the K. You would know that this would be a decay problem. Okay. Says a certain car was worth 30,000 when purchased and 10,000 3 years after being purchased. What is the decay rate? So the original amount is going to be 30,000. The 10,000 is going to be the amount after some time has passed. So we're going to put 10,000 here, 30,000 here. And we know that the time was 3. We don't know the K. All right, so we're going to go ahead and divide by 30,000 on both sides. I'm just going to get 1/3 here. And I'm going to make this negative 3K, you guys, so it looks a little nicer. Well, natural log. Just divide by negative 3. You have the decay rate. So K is approximately, let's do natural log of 1/3. And then I have to divide that by what, negative 3. So 0.3662. So probably, so if you move the decimal, well, let's leave it. Just wants to decay. If we had to turn it into a percent, depending on what my math lab's asking for, then you would move it 2 times. So it would be 36.62%. Oof, nobody wants to hear that as their decay rate and the value of their car after purchasing it, right? Okay. Write an exponential function to model the value of the car 2 years after its purchase. Well, it started off at 30,000. We know the decay rate was 0.03. No, sorry, 0.3662, right? No, 0. Sorry, I'm so scared. Okay, 0.3662. So now somebody can come in here, plug any time they want in, and figure out the value of the car. Estimate the value of the car. All right, you guys. Wow, we had so many different applications here. I'm hoping that you saw just how fruitful these logarithms and exponentials are out there in the real world as far as the numerous applications that they can be used in. All right, thanks for joining me, guys. Take care.